So now, the more important step, we need to formulate a proper model so that we can somehow write down some mathematical equations, and then we can solve the equations, and then we can have complete understandings to the transmission line. Okay? So, that's it. I'm giving you two wires that function as transmission line. So power can be delivered from the left to the right or from the right to the left. It doesn't matter. But the question is, where do we start? How can we start? It's just two lines. So the students watching, do you have any thoughts for how to start? It's very difficult, right? Because when I'm saying it is a transmission line, it means over the distance, I might have rapid changing voltage and current because the wavelength is short as compared to the transmission line distance. Okay. But what if I do some approximations or approaches? What if I dissect a very long transmission line into many, many short segments? Can I do that? Here I'm dissecting this transmission line into 4 shorter segments. Right? But in life, I can dissect even more. Okay. So the idea is a very long transmission line is equivalent to a lot of shorter transmission lines, but concatenated, connected. Okay? So the idea is I do have a transmission line, and I do have a high operational frequency. So that means along the line, I expect to see rapid changes in my waveform, right, voltage or current. For that case, I don't know how to formulate the transmission line. But the idea is that transmission line would be the same if I divide them into a lot of shorter segments. So if I zoom up a certain segment, so this is delta Z, and now this is delta Z. In this very short segment, the waveform change is really not that big. If I make my single segment even shorter, for example, even shorter, then the voltage change can be viewed, or current change can be viewed as a constant throughout the segment. Right? So that's the essence. In a very short segment, in a very short distance, the voltage and the current can be viewed as a constant. So when the voltage and current are both constants throughout space within the segment, we can very confidently formulate that single segment using lumped elements that we already know. RLs. Okay. So this is our building block. So now our job is to find the equivalent circuitry model for that very short transmission line segment. If we can analyze this short segment, all we have to do is connect a lot of the same identical short segments to recover the full length of the transmission. So that's the idea. Are we clear up to now? Any question from the audience? No? Okay, so I suppose I'm a very good teacher in that case. You have no questions. Okay. Now the question is, okay, so we understand the principle, we understand the philosophy. How do we start? For each differential segment, I'm using the wording differential because I want to dissect a long transmission line into a lot of shorter segments. So that's like making differentiation. Right? So for each differential segment of length delta z, I can view the left part as my input, and somewhere I have my output, right? So B prime, A, and A prime. So at this point, we need to ask ourselves, if you have a voltage or current traveling in the form of a wave over the transmission line, with certain time variation, so things are frequency dependent. So what type of phenomenon would you experience? In other words, we need to properly distribute R, L, and C. That's all we know, right? In electric circuit, the entire semester, you probably only learned 3 different elements: resistor, inductor, and capacitor, and that's it. So somewhere we need to insert those 3 different elements into the equivalent model, okay, to represent this very short segment. What does a resistor do to a voltage or current? If you have resistor, you have, right? What does resistor do? Resistor gives you loss, right? So you have energy loss. So in a real life transmission line, right? Like for example, the Tide Power delivers to us, but they always suffer loss, right? Because you have thermal transfer. Your electricity will be transferred into thermal energy, and that's loss. So can I properly insert some kind of resistance into the transmission line? So when your voltage is passing through, the voltage will be dropped slightly, meaning I have loss. Okay? On the other hand, can I also include some inductor? Right? Inductor also produces a voltage drop, but it will be stored in the form of magnetic field. But anyway, I'm trying to say that when I deliver over a very short segment of the transmission line, if I have a voltage, the voltage will be lower here, right? You start with a higher voltage, you have a lower voltage. And the two potential chances is to have thermal conversion or conversion into magnetic energy. But both gives you a reduced voltage. Okay? So can I include some inductance? Okay? Are you satisfied up to now? Up to now, we only used resistance and inductance. So the only thing left is capacitance. So now, your job is to tell me, or try on your own, how to include capacitor into that equivalent model. You have two choices. You have two choices by inserting the capacitance in that way, right? Directly connected in series. Or you have another choice, so the second choice is the connection of the capacitor is between the two metallic wires. So which one sounds more physical to you? This choice or this choice? And we do have two students here, so what are your opinions? Do you like this one or this one? I'm a very nice teacher. Whenever I ask, I'm trying to provide the answer already. So the one I'm writing more in detail, that's correct. Okay? So let me erase this one. But now you have to think. You really have to think. Why resistors and inductors should be connected from port in to port out in series, 串联. But the capacitor should be connected across the two wires in the form of parallel connection. Bing. So ask yourselves, in the past, in the knowledge that you already have, when resistors, I have one differential segment, don't ever forget, I actually have lots and lots of segments. I need to connect each and every one, right? Side by side. So resistors and inductors connected in series will give you direct summation. So if you have the equivalent model for a single differential segment having resistor and inductors in series, you add the second one, you add the third one, eventually you recover the full resistance and the full inductance. Because resistance and inductance adds up directly when connected in series. On the other hand, capacitance adds up directly when connected in parallel. Okay, so this is some background information you already have, but now it's really implemented in a real case. So up to now, are you satisfied? For generality, we need to also include something, well, some leakage current. So this G is equivalent to R double prime over 1. Right? The inverse of the resistance is called conductance. It's viewed as a leakage current. Why am I including this term? Because although these two wires are acting like independent conductors, but sometimes current can leak through from one conductor to the other. Right? So if you can have current conducting, that's called leakage, 漏电流. And then correspondingly, you would have a conductance in that path. So this is the proper lump element circuitry for a differential length of the transmission. So now I can safely add the second one, a third one, right? To represent the real transmission line. But for each differential segment, they are looking like this. They have identical parameters. Okay. So this page is only for your reference. If you don't remember, in the time domain, V across a resistor is V equals IR. For an inductor, the voltage across the inductor, VL is L di dt. So you need to have time varying current to produce a voltage drop over the inductor, right? Voltage drop. So voltage drop. We have a frequency dependent or time dependent wave. So when it meets the resistor, you will have voltage drop, right? If you have a capacitor connecting between the two wires, you can have some kind of current drawing functionality, and that current is C dV dt. That's something you know already. But personally, I don't like to solve things in the time domain. So now you have differential equations. But as we talked about on Monday, if we use the phasor representation, we convert everything into the frequency domain. Derivatives become directly multiplication of j omega, right? Then you don't have differential equations anymore. You only have algebraic multiplication, adding, subtraction, that's it. Okay, so in the end, I want to use everything, if possible, in the frequency domain using phasor representation. Okay, so you're already home. After the class, try to familiarize yourselves with this transformation. Okay. All right, so on the right bottom blank space, that's a place for you to fill in this, the equivalent model using lumped elements. Okay? And here, R prime, G prime, L prime, and C prime are the resistance per unit length, G prime conductance per unit length, inductance per unit length, and capacitance per unit length. Because eventually we dissected the transmission line into many, many small segments. So here, I need to have the total resistance divided by the whole length, and then times delta Z, right? So the total resistance is the resistance per unit length times the length, the differential length. Okay? Is the model reasonable? That's the question, the big question you have to ask yourselves. Again, capacitors adds up. So the first differential segment will be connected to the second differential segment. So the capacitors, they are connected in parallel, they directly adds up, right? So if you connect 1,000 differential segments, eventually the C value all add up as you connect one by the other. Resistors and inductors also add up in series. So this is the reason behind. The equivalent model, you need to have resistors and inductors connected in series, but capacitors connected in parallel. Okay. So if you have no questions, let's stop here today. But starting from next week, we will use the equivalent lumped element model, and we will be involving mathematical derivations. So as I said on Monday, this class requires your devotion. You need to preview the course material and review the material, right? So think about it. Even though we know the model, where do we start? How can we write down some mathematical formula? So that will be explained next Monday. All right? Good luck.